Hi everyone, all right. I think it's about time for our wonderful second plenary speaker, so I'd like to encourage everyone to grab a seat. If you're outside and can hear me, please consider being inside. It is my absolute pleasure to introduce John Barron. John is a senior staff research scientist at Google Research in San Francisco. He works on computer vision and machine learning. He got his PhD at Berkeley, so that's a big plus in my book, with working with Jitendra Malik in 2013, and did his undergrad in Toronto. Lots of distinguished things which I will skip because everyone would much rather hear John speaking. So John, thank you very much for coming.
Thank you. Hi, everyone. Hey, it's really great to be here. Thanks for the invitation. I have a lot of econ professors in my family, so it'll be fun to talk about the Hoover Institute giving a talk here. This is neat. So I'm John, and I'm going to be talking about neural radiance fields. I'm not really going to get into robotics specific stuff, but I feel like the robotics applications are kind of straightforward. So I'm more going to give like an intro, high level about like what this stuff might be useful for, what it's useful for today, and what it could be. So just quick review about me. Did my PhD at Berkeley with Jitendra, who's right here. He is now a roboticist apparently, which is neat. I spent most of my research career just trying to do vision with graphics. In my undergrad, I took the vision class and the graphics class, and I thought it would be easy. I could take them at the same time because it would be the same thing, just forward and backwards, and it wasn't, and I got very frustrated, and I said, someone should fix this. So I spent a lot of time just writing down a rendering engine and implementing the gradients in MATLAB, and then trying to backprop through a rendering engine. And it didn't work super well for a long time. In grad school, it kind of worked, and after grad school, I went to Google. Actually, I joined Google X. Sebastian Thrun was my boss's boss when I joined. And I worked on a bunch of things, but I've kind of come back to this, again, just doing vision by doing graphics in reverse, and NeRF is probably the best example of that now. So just a quick overview. I'm assuming you guys are all roboticists. You don't really know graphics. I just want to lay down some kind of ground terminology. Graphics, what's graphics? There are like two kind of primary paradigms in graphics. One is rasterization. This is what every interactive video game you've ever used does. And you can think of it as I want to make an image by doing a for loop over triangles in the world. And for each of those triangles, I'm going to kind of project it onto the image. And there's another paradigm, which is ray tracing. And this you can think of as a for loop over pixels in the image. So for every pixel in the image, you shoot a ray out into the world and you see what it hits. This is relevant because NeRF is a ray tracer, and that's a critical part of what makes it work. Another paradigm, another kind of split in graphics is the thing you are rendering. And most of the time when people think of rendering something, they think of a triangle mesh, this mesh rendering paradigm. This is by far the most common thing. This is what almost everyone does. You've got a bunch of triangles in the world, and they are these hard, colored, textured things, and you render them. There's another paradigm that used to be more popular and then kind of went away, which is volume rendering, where the world is not made of these hard triangles. The world is made of this soft, fuzzy, mushy stuff, usually like a voxel grid, a tessellation of 3D space, where everything is semi-transparent and everything is kind of mushy. So NeRF is a volumetric ray tracer, and that's kind of like the secret sauce for getting this stuff to work. So what is NeRF? So this is a paper from almost 4 years ago now. A NeRF is a neural radiance field. Neural because there's a neural network, radiance because that's the thing we're modeling light, and field because that's a calculus term. It's a smooth function that you can query. And NeRF, this project started its life in terms of this problem of view synthesis, where we want to take a bunch of images of a thing and then make new images of that thing. And the easiest way to do that is to reconstruct a 3D model and then render that 3D model. And that's what we've been kind of focused on. But over time, I think the takeaway from NeRF is that it's a very, very good 3D model for gradient-based optimization. A NeRF is just a 3D model that is amenable to gradient-based optimization. So at its core, every NeRF is a simple, tiny little function. In the first paper, it was a simple neural network. It's since become varied other things, but these are all just smooth black boxes that you can get gradients of, where the input is 3 numbers. So it's just X, Y, Z, where am I in space? And the output is 4 numbers, RGB, a color, and then a volumetric density sigma, that's 0 to infinity. 0 means this space is completely empty, this would all be 0, and infinity would mean this is a hard wall. So if you have one of these neural networks, if you have a trained NeRF, the way you render an image from it is you take a camera You take a camera that has a well-defined position, it's these little triangles there, and you pick a pixel in that image you want to render, and you shoot a ray from the center of that camera out into the world, and then you grab a bunch of XYZ coordinates along that ray. That's what those black dots are there. And you can imagine taking that n/3 matrix, that's a batch, you push it through this neural network, and on the other side of the neural network you get a bunch of colors and densities. And then you can run what is it's called alpha compositing. It's just the correct solution to how to render semi-transparent things. So you walk from the back of the ray to the front, and if something is very opaque, if something is very dense, it clobbers the thing behind it. And if something is empty, you do nothing. So you walk from the back of the ray to the front, and when you're done, you have a color that's the composite of all of those colors along the ray, and then you render that pixel, and you move on to the next pixel. So that's what you would do if someone gave you a trained NeRF, and the way you render a NeRF is you just initialize one of these models randomly, or you can, in some cases, you can initialize them to be all zeros. Being random is not that important. And you just repeatedly render an image corresponding to some input images someone gave you, and you minimize squared error, absolute error between your renderings and the observation. And the weird thing about this is that if you do this like a billion times, you will recover a 3D model of the world that is parameterized in the weights of this neural network in that theta. And the secret sauce here is that this is a volumetric ray tracer, and I think the core insight of NeRF is that this observation that volume rendering, the math behind volume rendering, is differentiable. So if you sit down and you implement some volume rendering paper from 1995 in PyTorch or JAX or whatever, you will be surprised maybe to discover that it's a bunch of soft pluses and a bunch of sigmoids, a bunch of things that are just correspond to well-behaved deep learning primitives that work well. So NeRF really works. This is results from the first paper that caught a lot of attention because these sorts of 3D reconstructions were not things that people were used to seeing. NeRF can recover shiny things and thin things and all sorts of subtle effects that result in the renderings looking like images, which really wasn't the case before this work came online. And the roboticists were particularly interested because you can render images from these models, but you can also render depth maps. And the way this works is you can imagine that for every pixel you kind of shoot an arrow from a bow and arrow into the scene, and you measure how deep into this foggy neural thing it travels. If you do that for every pixel, you get a depth map. And these are really finely detailed depth maps with lots of thin structures and very clean edges. And I remember getting a DM from a roboticist at Google saying, like, I don't know how to ask this question, but do you understand that these are very good depth maps? And I was like, yes, we understand it. So I think a lot of roboticists at first were like, oh, we can have good depth maps. And that has been a lot of the early work on NeRF and robotics. There was a kind of sea change in NeRF about a year and a half ago, where I originally just described this as a small little neural network. And that works fine, but it's a very kind of awkward representation for these scenes. And a lot of people have since pivoted to what here I'm calling NeRF v2, but no one will call it that outside of this talk. There's an alternative way of doing this where that's maybe conceptually simpler to think about, where instead of having this MLP that maps coordinates to colors, you can just have something like a very large voxel grid, where you just kind of directly store densities and colors. And this is in practice what people are doing much more these days. And the upside of this is that if you just directly store a color and a density in this grid, you can render the scene very efficiently by just looking up these values in this grid, as opposed to evaluating a dense neural network. So there's this kind of a continuum of techniques that have emerged. I won't go into details of how these all work, but a lot of the papers you'll see in the space are somewhere on this continuum of either you can have a very, very compact little MLP that's very expensive to evaluate, or you can have a very big representation that is much more like an explicit voxel grid that is cheap to evaluate, but is painfully big. And yeah, for the first NeRF paper, it was surprising because this MLP was, I think the reason this work caught a lot of attention is that in the first paper, we took a very extreme approach of having this very small neural network where the network would be, in practice, smaller, significantly smaller than all of the images that had been used to train it. Which was counterintuitive and kind of impressive at the time. All the results you saw just now were from a model that had 5 million parameters, so 5 megs of weights. So pushing on this NeRF v2 thing has been very productive in terms of quality and speed, and this is where we are now. This was a paper that my team presented at ICCV a couple weeks ago, and we're now at this in the situation where we can render really, really nice, mostly photorealistic renderings of pretty large, complicated spaces with lots of stuff going on. This is my house. It's a little awkward with my wife right now that I've been using my house for this, but it was space that we can get rights to without worrying about it. This video went viral on Reddit when we put the project page up, and I don't have any control. The computer vision community has a social media ban, so I couldn't do anything about that. But it was the Be Amazed subreddit, and the title was "An AI Generated This House," which is like kind of true. And Reddit commenters have a range of understanding of this. So my wife and I were scrolling through the comments and seeing things like, "You can tell this house is AI generated because it has way too many chairs." Like, that was a fun Saturday. Again, a NeRF is just a 3D model, right? It's a weird 3D model that's kind of represented with this entangled volumetric neural thing. But at its core, it is a 3D model. You query a point in space, you get a density, and it's physically consistent and meaningful. It's just a very expensive 3D model. It's very awkward to render. We do it using Jack's code on a TP or whatever. But you can take these models and just turn them into a conventional 3D model. So here these videos should be looping, but they are not. Here I'm rendering. We've taken one of these models and we've turned it into a textured mesh, the same thing you'd see in a video game, and we can render them in real time. If you go on this project page on your phone, you can actually render it on your phone in real time. Feel free to do that, I won't be offended. And because this is a 3D model that's just a real 3D model that's compatible with any video game engine or whatever, you can just do whatever you want. You can retexture it, you can integrate it into various lighting systems and stuff like that. And yeah, this stuff has had real impact on the world now. Google Maps launched NeRF, basically. Sundar Pichai presented this at Google I/O almost 2 years ago now. You can try it on Google Maps on your phone if you take a picture of that QR code. They sent out some photographers to photograph the insides of lots of nice restaurants and NeRF the insides, and now you can scoot through them on your phone. It's fun. So that's kind of NeRF a little bit. And I think it's helpful to talk about like how to frame this work in the context of other work that's kind of related, because there's a lot of terms that get thrown around here, and I think the distinction between these techniques is kind of subtle, but worth understanding. And one big shift that we saw with NeRF was kind of this shift in the meaning of like neural rendering, which was a field, this was an area of study in vision and graphics. And this used to mean a neural network renders. A neural rendering was a neural network that rendered, people would train a model that would take in some feature mask type thing, like a depth map and normal maps and stuff like that, and the output of the model would be a rendering, a bunch of RGB values. And this is a totally reasonable thing to do. It's a little weird, but it works really well. And the kind of shift that NeRF represented was in terms of what this has begun to mean, which is a very different paradigm if you think about it. So this is still a neural rendering. There's a neural network that is contributing to this rendering, but the neural network is not parameterizing the process, the mapping of geometry to color. It is parameterizing just a 3D model, and the thing that renders it is just a normal rendering engine. So this model is not in charge of learning how image formation works or like making guesses about color. The model is just gradient descent is just trying to recover a 3D model, and the mapping of that 3D model to an image is just physics. It is just a light moving through space, a ray bouncing off of stuff. And I think this is probably very good because it means the model doesn't have to go through the painful process of learning a bunch of physics and geometry from scratch. It's just imposed in a top-down sort of way. I also want to contrast this with other work that's been going on in this space, which is, I think, really cool and underappreciated. Another thing you could do that's kind of like NeRF is you could take a ray tracer. So like ray tracers are a very mature technology, right? Like every Pixar and Marvel movie you've ever seen has been rendered with these things. 30, 40 years of effort has gone into building these systems, and they are incredible. And these graphics people have done this extra incredible thing, which is just take a ray tracing engine and just build AutoDiff into it, which is incredibly hard. But it's really cool that you can do this. You can take like a Pixar rendering engine and just backprop through it. It was a tremendous engineering challenge to accomplish this, but they did it. You should check out Mitsuba 2 and Redner. The problem is this doesn't work. If you just take a rendering engine and you push gradients through it and you try to do vision by doing gradient descent on a Pixar 3D model of a scene, optimization fails catastrophically because this is just an incredibly poorly behaved optimization space. And you can think about that in terms of like, I have a triangle in space and I want to make this thing red and this triangle is red. The gradient that propagates from this red pixel onto this triangle over here is 0. There's no signal that gets communicated that way. And equivalently, if there's a triangle in front of another triangle and you do gradient descent on that, the triangle in front will just kill the gradient, right? It won't propagate to the thing behind it. So this is a very cool line of research that doesn't work yet. And NeRF represents like a very different approach to this, right? Where we have the world's worst rendering engine. We have like an archaic and oversimplified rendering engine, but we're building it up from scratch, from the bottom up, using just the tools of differentiable programming. And what that means is that you have a model where gradient-based optimization works really well. The problem is that we're kind of in this process of reinventing all of graphics from scratch, where we don't have anything. We have an extremely simplified 1970s model, and we're kind of moving through the 70s and the 80s and the 90s. I think we're in like the mid-90s now. Sorry, they didn't allow water in here. If anyone has a bottle of water, I'd appreciate it. So I've been mostly talking about NeRF in the context of this conventional photogrammetry task, where we have some images and we want to reconstruct those images in a 3D model. But like I said, NeRF has kind of become a general purpose 3D model for any sort of gradient-based optimization thing that you would like. And this is well represented. This is, I guess, a bit far afield for robotics people, but I think it's an illustrative case study. This was a paper we had at iClear this past summer, or spring. And I showed this picture where we're trying to recover NeRF by minimizing the difference between the rendering and a bunch of images. But you can instead just forget about that and say, oh, actually, the objective that I care about is not how well does this rendering match this image, but just how well does this rendering match this text description, for example. So to do this, we're building on diffusion models. And I'm not going to go into detail about how diffusion models work. If you don't know, I'm going to be like a really bad person to teach you. But the central problem with diffusion models is that the optimization lives in the same space as the sampling. So the way diffusion normally works with a 2D image is that you initialize your image and you push it through a CNN 30 times or so. Oh man, you're the best. Sorry. Oh. Talking is like, oh man, so draining. Okay, so if you are running a diffusion model on an image in the kind of traditional paradigm for image synthesis with a 2D diffusion model, what you'll do is you'll initialize your image to noise and you'll apply a CNN to it like 30 times and it'll just update in place. And this is a great system. This works really well for image synthesis. The problem is that these tools only allow you to do inference in a space where your model and the convnet that's powering your diffusion model and your model of the world, which in this case is an image, they have to be in the same space, right? You've got an image and you've got a model that expects images. We don't have that. We have a model that expects images and we have a rendering engine. So you need to take these diffusion models and kind of modify them so that you can basically treat them like a black box that emits gradients. And I won't go into details of how we do this, but there's a trick for doing this. We figured it out and you can use it now. So the way this works in this Dream Fusion model is we have a 3D model that's initialized randomly. And I'm not going to go into the details of how that model works, but you can think of it like a toy rendering engine with a NeRF in the middle where there's lights and materials and shading, which is a little bit more elaborate than the normal NeRF case, but functionally the same. And we're just going to repeatedly render it from different angles. We're going to look at it from over here and over here. And every time we look at it, we're going to say, hey, does this look like a picture of a peacock on a surfboard? And if it doesn't, we're going to nudge it the way like a sculptor would kind of draw some paint or chisel something in to make it more like a peacock on a surfboard. So you get this rendering, you add noise to it, you feed it to someone else's 2D diffusion model. We used Imagine, which is a very nice model that Google developed about a year ago. We don't want to train these models ourselves. We're just taking them off the shelf. So these are frozen weights of a text-based image diffusion model that we're using like a prior. And then you get this rendering, you get a gradient, and you backpropagate it onto your NeRF. And you just do this like 5,000 times, and it works. And we can look at that. So here is inference of a NeRF. that is slowly coming into focus as a peacock on a surfboard. And this is a real 3D model. It's a 3D model that's parameterized by a NeRF, but it is as 3D as a mesh, and you can just look at it from any angle, and it works fine. And I want to reiterate that this model has never seen 3D before, right? This is just a NeRF and a 2D diffusion model that has been trained on like 1 billion images. Oh, geez, talking. So yeah, this is what results from this model look like. We just, we went nuts one day and just came up with every prompt you could think of and solicited prompts from people across Google. And it's fun to show these because this is obviously like very cool and neat that this works. But also, like, I really want to reiterate that, like, this is some weird stuff. There are like combinations of things happening here, like an alligator playing drums that, like, these are definitely not in the training data, right? It's worth being on guard about this because it's very hard to make a 3D synthesis model, especially one trained on only 2D data that has this sort of diversity of things being mixed and matched. And yeah, these are real 3D models. You can play with them on a website, scroll them around. We put this online, and within like a day, people were putting these into video game engines and 3D printing them. It's neat. And this work kind of led to a real explosion in this space of 3D synthesis. This is something I saw online this past week that really blew me away. I have nothing to do with this project, but like, holy cow. And yeah, and that's it. Thanks.
Thank you very much, John. We've got some time for questions. I'd like to encourage you, if you have a question, to come up to one of the mics to ask. If I can maybe exploit my... Oh, Frank, go ahead.
Is this your new house?
This is actually an Airbnb that some people at Google rented to have a pretty place to photograph at some point. We never released this video. You should all feel very privileged for seeing this video because we never put it online because we didn't think we had the rights to redistribute this Airbnb. But I use it in talks because it looks cool.
Thank you for the talk. When one is collecting data to build a NeRF out of, how critical are the camera locations? Do those have to be known, or can we just do the sort of roam in a day style? Thank you.
So roam in a day, so they're doing bundle adjustment. They're solving for the camera poses from the images. And that's what we do as well. We use like a structure for motion package, call map, to reconstruct poses from the images. We have no metadata or whatever. I don't know how you really get ground truth poses per se, but if you tried doing it with something like ARCore or ARKit or odometry or something, the precision you would get would be nowhere near good enough for these models because if you just work through the math of image formation, like a millimeter offset will really change where those rays are coming into the camera and where the pixels should be. So yeah, having well-posed cameras is absolutely critical for this stuff to work. You can kind of solve jointly for the NeRF and the cameras. We have a paper on that came out. It's coming out this month. It's on archive, but it's still kind of a hard problem. Yeah.
Yeah, I wanted to ask about those that whole slew of 3D images that you had out of the diffusion
Yeah, let's
models.
bring that back.
They looked really nice, and so I was wondering, these diffusion models have issues with hallucinations, or weird aspects. Do you still see that in your output, or does the 3D rendering help with that at all?
So what we're doing here, right, is we're running one of these diffusion models thousands of times, and so if it starts making weird guesses, they'll kind of get averaged out into more these are kind of like the platonic ideal of one of these queries. The diversity is very low. Like if you ask for a squirrel, you'll always get the exact same squirrel, and the 3D nature of this is kind of a forcing function for that. But we do still see tons of artifacts. A common artifact we would see here, which we call the Janus artifact in the paper because of the multi-headed god, is you would ask for something and it would make that the front of that, but then put a copy of their head in the back because it would look at the thing from the front, say that should have a face on it, then look at it from the back and say there should also be a face here too. This would look more like a squirrel if there was a face on the back of it. So there's no shortage of artifacts. Lots of work to be done in this space still.
Thanks.
So we have 4 years of development of the NeRF to handle all the static objects and static scenes. which has already pushed to some extreme. What about the dynamic objects? Are there any ways we're going to handle those so that we can build both the static and dynamic artifacts into the scene? Yeah.
Dynamics are a ripe area here. There have been very many papers on dynamic NeRFs, and they show some, there's been some success for cases like a person. We had one paper where we took selfies, we called them NeRFies in the paper, where we just waved a camera in front of our face and kind of articulated our face. And it can kind of be tolerant to that. But then the harder cases of cars going down the street or whatever, it becomes like a much more difficult problem. And I think that in general, this deformation problem is pretty open still.
So do you think additional sensors like LiDAR will help further to handle those issues?
Yeah, it helps disambiguate whether something is due to motion or not. But I think there is still a central problem of like, how do you represent a world that is made of parts of things that are moving around? And people have these like kind of scene graph NeRF type models where there's like a mixture of things moving around. And it works, but it doesn't feel like we have the final word on exactly how that should be parameterized.
Okay, maybe some quick questions still.
Yeah, actually, it's a similar question, but you mentioned robotics was excited about NeRFs because of depth. Is it good enough to let's say, work with a robot and use NeRFs to estimate depth, or do we still need other sensors to be accurate enough?
It's good enough in some sense in that the renderings look nice. So I think this stuff is most useful in robotics context for simulators that are made from real images and so look more realistic. None of this is real time, right? Like, so the reconstruction is slow. It'll take 20 minutes to reconstruct a house. So if a robot's moving through the house and moving stuff around, if you're interacting with the world, I think that's still an open question. There's also, our depth maps are often quite wrong in a way that looks good when you look at the images, but really will frustrate roboticists. Because if you have a mirror or a shiny surface, the NeRF reconstruction will usually make a mirror world, so it'll make an upside down copy. Like if this floor is shiny, it'll make a copy of what's up here below the surface that I can kind of see through the semi-transparent surface. It looks great, right? But the roboticists look at the depth map and they see giant holes in the floor. So it's a bit of a problem for that.
Those are great work. I have a similar question as the last two questions. Since this is a robotics symposium, and I was wondering, given that the low-level aspect of things is very important for robotics, what do you think is a bottleneck right now that prevents NeRF to be applied to robotics at a larger scale?
I guess probably speed. Like, a lot of these things would be much more useful if you could do them and like have things update dynamically and interactively. But I don't know. I feel like robotics is hard in so many more ways than vision is hard. But I doubt, like, you know, I think that there's no shortage of problems to making this stuff useful. I'm not totally convinced that this is the secret sauce for solving robotics either. I think it's just a useful tool. I am optimistic, though, on this. So a lot of these robotics papers that use NeRF just use it as a different vision system. They just say, here are different depth maps, whatever. But I think that there's probably more you can do if you just think of these as general purpose 3D models that you can do gradient-based optimization on. And I bet there's something in robotics land that is solved by this insight. The same way we were surprised by how it was useful for generative, I feel like it must be surprisingly useful for robotics in some way that we haven't figured out yet. So I don't know.
Okay, we have time for one very quick question still, and then Mac, I think maybe if you can come sit up already.
Great, thank you so much for the great presentation. I have a question about how well NeRFs can do when there's occlusions or limited viewpoints for certain objects, especially for robotics. You might not see every view of the object. How will it handle it, and how is it very obvious for the robot which parts are uncertain?
There is some stuff that you can do. Here, I'll unplug so you can keep. There's some stuff you can do about modeling uncertainty in these models and get like a measurement of like, oh, I don't know what is here. But it's still early days and none of those techniques are super, I don't think we have the final word on that. These techniques are all very data hungry. So if you have, please start. If you have not enough data, you will get artifacts. And a lot of the results I showed have like hundreds of images. So data scarcity is a problem. I think that the work you saw in generative could maybe patch some of those holes, but we don't totally know yet.
Thank you.
All right, excellent. Thank you very much, John. And I'd like to ask everyone to join me.